Hi everyone, in this second part of the ring permeameter video, I'm just going to talk through what we do with the data we've collected. I'm not going to go through the theory in this video, but just to tell you practically what you do with the information you've collected in the field. So let's have a look at the spreadsheet that you should all have a copy of. We have the site that we're going to be working on. You can see here we've described it as in wood below the nursery at the university, and the date that we collected the information. We then have a table which has the measurement number. This is just the sequential number for each of the measurements. We have a column here called unstable level. So these are the early measurements that we take before the level stabilizes. And so often when you start these experiments, there's a kind of a big rush of water into the ring at the beginning of the experiment, and so the level is unstable. So we don't really want to use those in the calculations. We've then got minutes, seconds into the experiment, and then the cumulative time in seconds. And then all we've got in the final column, green one here in the spreadsheet, is the level in the top tube of the infiltrometer in millimeters for each of the time intervals. So you can see here where that's been recorded, and you can see the level dropping down through the experiment. Now, if you look to the right, the spreadsheet has plotted this on a graph. You can see the level here, and you can see the time. So you can see the falling, steady state fall in the level represented on the graph. And we fitted a regression line to that data, and you can see the equation from that line is here in the top right-hand corner of the graph. Note the gradient, minus 5.2, because we're going to be using that in a little while to help us with the calculations. Right, I'm just going to scroll down now, and we're going to have a look at the calculations. Okay, so this is where the 5.2, which is the gradient of the line in the graph, fits into the calculations. It's the discharge in centimeters per second through the core. We then got the core length, which is 9.9. So this is the length here, where between the soil surface and the base of the steel ring. We then have DH or D head, which is the length of the core plus the constant head. So this is the bit above the soil surface to the base of the ventilation tube, which is the constant head that's going to be applying pressure to the soil surface. We then have the cross-sectional area of the ring. So this is 720 square centimeters. So this is the cross-sectional area of the kind of the coring, the steel ring, and then the cross-sectional area of the top tube. So in this case, it's for just over 43 square centimeters. We can then use that together with the water temperature in centigrade, the viscosity, which we can get from a table of the water, to calculate the saturated hydraulic conductivity. In this case, 858 centimeters per hour, and we can obviously convert that to the saturated hydraulic conductivity at 20 degrees, which gives us 974 centimeters per hour. And that's using the equations in the Chappell and Turnen paper. So that's how you use the spreadsheet to calculate saturated hydraulic conductivity. Good luck with your measurements.